Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 6, Part 3. Okay, now that we have compounds that have stereocenters, and stereocenters are those things that have four different things bonded to the carbon, typically. And we also know that if we have two stereocenters, we end up with a pair of enantiomers that are mirror images of each other, and then another isomer that creates a new pair of enantiomers. Okay. Now we're going to apply these rules of chirality to cyclic compounds and start adding those planes of symmetry to them to see whether or not these compounds are true diastereomers or whether we have enantiomers and meso compounds. Okay, so like before, if we have two stereocenters, that means we're going to have 2 to the power of the number of stereocenters equal the number of stereoisomers possible. Okay, if they have an internal mirror image, they're meso, and that means that increases the number of isomers we have. Okay, so in this case here, we have 2 stereocenters, so we have 4 stereoisomers possible. Let's see how much of them actually exist, okay? So just drawing out one of the compounds here, right here, let's draw this where the methyl group and the OH group here are cis to each other. And then we drew the mirror image of it here such that our methyl group is sticking out here and our hydroxy is sticking out here. This would give us our mirror plane in between our 2 compounds here and give us our correct drawing of our other enantiomer, our mirror image that is associated with it. But to make our other pair of enantiomers, we'd actually have to swap 2 of the groups. So we're going to swap this hydroxide and move it to the back here to generate this isomer here. Our methyl group is still forward, but our OH has been put to the back to give us this. And then if we used our mirror plane and generate our image of that, we would have the hydroxide in the back and our methyl group in front. So here is a pair of enantiomers for the trans derivative where the hydroxy and the methyl group are opposite each other. And here is the pair of enantiomers for the cis isomer where the hydroxy and the methyl group are both on the same side. And again, we like to do these things with cyclic compounds because we don't have free rotation. And so it's going to lock in that position so we can make it easier to make sure we have the correct isomer without having to worry about all the different free rotations around sigma bonds. Okay, so let's do it again, but for cyclopentane dial, okay? Here, because we have 2 different alcohols, we do have a total of 2 stereocenters, and with those 2 stereocenters, we have a total of 4 possible isomers, okay? But let's see if they do exist or not, okay? So if we look at the first isomer here, the first isomer is with both hydroxys on the same, and if we draw the mirror image, that would give us this here. If we look at the trans compound here and we draw our mirror plane, we get our pair of enantiomers here. Now, if we tried to superimpose this one on this one, we actually cannot do that. They do not rotate around enough to superimpose. They do not have superimposable mirror images. Therefore, we do have a true pair of enantiomers on this side. However, if we took an imaginary plane of symmetry, drawing it through that carbon and halfway between the bonds here, the hydroxy on the top would mirror the hydroxy on the bottom. This methylene would mirror this methylene, and this carbon would be cut in half right here. Meaning that because we have this plane of symmetry, that means all we have to do is rotate this one 180 degrees and they would move it over here. It would become superimposable, okay? Because of that plane of symmetry, that material is superimposable. Therefore, it is not a chiral compound. This particular isomer is a meso compound because of that plane of symmetry. So in the case of the cyclohexane, we actually have two pairs of enantiomers because we do not have a plane of symmetry and we cannot superimpose the mirror images. In the case of the cyclopentane dial, we have a plane of symmetry. Therefore, one pair is actually a meso compound of one compound. The other set is actually a pair of enantiomers and brings us to a total of 3 isomers. Okay, let's do it again for this cis-methyl cyclohexanol. So we have a cyclohexane, and we have a methyl group on one side and an OH on the other, and they're both sticking out toward us because of that. When we look at this plane of symmetry, that means this carbon matches this carbon matches this one. This half of this OH is above the plane and below the plane. Half of this methyl group is above and below the plane, okay? Which means the cis compound here is achiral. It's mesochiral because of this plane of symmetry, even though it's cutting through atoms. It can be either cutting through bonds or cutting through atoms or both to do this thing. If we look at the trans isomer, notice the methyl group is now on a dashed wedge, so it's behind the plane. The OH is out in front of the plane, so it's the other isomer. We can still generate that plane of symmetry cutting through the methyl group and cutting through the alcohol group, the OH group, to give us a mirror image. This side looks like that side, this side looks like that side, and half of each of these molecules is above and below. That means this compound is also meso, okay? So we have not 4 chiral isomers possible, we actually have 2 achiral isomers. The cis isomer is achiral because of the mirror, the plane of symmetry. The trans isomer is meso because it has that plane of symmetry. Therefore, neither compound is chiral, even though it contains 2 stereocenters. Okay, so what if we changed it into a different isomer? Now we've had them in the 1,2 positions, we have them in the 1,4 positions. Let's look at these 2 compounds that have it in the 1,3 positions, okay? So in this case here, we have a methyl group and a hydroxy group here, and they're on the same side of the ring here. They're both sticking out of this. And if we draw our mirror plane in between them and have it so this is pointing out and this is pointing out, we actually have something that is non-superimposable. There's no, if we draw the mirror here, the hydroxy is mirrored. If we draw the plane of symmetry here in the middle, the hydroxy is going to be in the same place as the methyl group, so that's not a plane of symmetry. We can't draw the plane of symmetry here. We can't draw the plane of symmetry here because this doesn't match that. We can't draw the plane of symmetry here because the groups aren't on the same side. We can't draw it here or here. So we do not have a plane of symmetry in this compound, and therefore we do have a true pair of enantiomers. Now, to get to the other isomer, we have to switch one of the groups. And in this case, we're going to take this methyl group here, and instead of being a solid wedge, we're going to turn it into a dashed wedge, keeping the other group the same. So we have the OH is going to be the solid wedge, and now the methyl group is the dash wedge. And when we do our mirror plane, we have a dashed wedge going here, we have a solid wedge going here. And just like before, if we tried to create a mirror or a plane of symmetry here in the middle, the OH is going to be sticking out toward us down here. The methyl group is going to be behind us back here. So there is no plane of symmetry here. There is no plane of symmetry through the middle of this. So therefore, that means we have a new pair of enantiomers, okay? So we have non-superimposable mirror images. We have no planes of symmetry in either compound. So we have a pair of enantiomers, a pair of enantiomers, and the set of all 4 of them is our set of diastereomers. 2 stereocenters, a set of 4 stereoisomers. Okay. So let's look at that other isomer. Instead of the 1,3, let's go to the 1,2. Okay, so now let's do the same kind of analysis we did before. Outside wedge, outside wedge. So when we draw our mirror image, we have outside wedge and outside wedge. If we did a plane of symmetry somewhere, let's see if we can draw a plane of symmetry. So the OH would match that and that. So there's no plane of symmetry here. So that means this is, yes, two stereo, this is a pair of enantiomers. Now, again, to create the other pair of enantiomers, we take one of the groups and switch it. So we've taken this solid wedge and turned it into a dashed wedge. And now we use our mirror plane here to generate our OH in the back, our methyl in the front. Now let's try to create a mirror plane somewhere in this system here. If we do this, the OH and the methyl don't mirror each other. If we do this, the OH and the methyl don't mirror each other. And again, if we do it here, then there's no methyl group over here. So there is no plane of symmetry in either of these as well. So this particular isomer also has a set of 4 stereoisomers. It has 2 pairs of enantiomers. One is going to be the cis, one is going to be the trans. Oops. Okay, so let's look at the 1,3 derivative as well. And what we'll see here is when we have the cis compound of the 1,3, when we do our plane of symmetry, we have this OH sticking out at us, and we have this OH sticking out at us. That means that if we were to look at this plane of symmetry, this OH is out and this OH is out. They mirror each other. They would be in the same plane. They would be in the same position on either side of this plane of symmetry. That makes this one a meso compound. Okay, so if we were to try to draw the other isomer, we have to flip one of these around. So we're going to keep this one as our solid wedge, turn this one into our dashed wedge here. And when we make our mirror image here, it creates these 2 images here. So we have our mirror images, and they are non-superimposable, because if we drew that same mirror plane, that plane of symmetry we had before, right here, this OH would be on the outside, not the inside, and this OH would be on the back side, not the front side. Therefore, there is no plane of symmetry in this set, but there is a plane of symmetry on this set because both OHs are on our side of the plane. Therefore, this is a meso compound, and this is a period of enantiomers. So the total number of isomers possible are 3. The cis isomer, which is meso and non-chiral, and the trans isomers, which will give us a pair of enantiomers. Okay, so how many stereocenters are present in the molecule on the left, and how many stereoisomers are possible, and let's assign them all. Okay, so let's look at this compound here first, right here, and what we'll see is that the first thing we're going to look for is the carbons with 4 different things bonded to them. So let's start counting that, okay? So if this carbon right here, it has 2 hydrogens on it, this carbon has 2 hydrogens on it, this carbon has 3 hydrogens on it, this carbon has 2 methyl groups on it, 3 hydrogens, and 2 hydrogens. So none of these carbons do we have to worry about because they all have at least 2 or more of the same group bonded to them. Okay, so that leaves the other 3. The oxygen here only has 1 other thing bonded to it, so it doesn't have 4 things bonded to it. And so we don't have to worry about that. So let's take away all those. So now all we have to deal with is these 3 bonds here. These 3 stereocenters here. 1, 2, 3. Okay, now, given this structure here, we are given, it's drawn in such a way we don't know which particular isomer we have. So what we have to do is we have to pick that isomer now that we have those 3 stereo centers, we have to identify which isomer we have. And we do that with the wedge configuration here. So in the case of this here, we've identified the specific isomer by showing us where our wedges are. So the isomer we have here for this is the solid wedge for methyl. So this CH3 is coming out at us. We have the solid wedge for the OH, which means the OH is coming out at us. And we have the dashed wedge for this group right here. And so that's going back into the plane. Okay, so this specific isomer is one of the possible isomers of this compound here. And so we're going to identify each of those compounds. Again, we have a methyl group here. We have 2 CH2s, but then we have a CH2 with a carbon on it and a CH2 with an O on it, which makes this our #1 priority side. This is our #2 priority side because it's a carbon with another carbon bonded to it. This is a carbon with just hydrogens on it, which makes this our 3. And that means that dashed last hydrogen here is our 4th priority in the back, okay? So if we look at our hand again, and we have our hydrogen back here in our 4th priority, our 1st priority is where our thumb is, our 2nd priority is where our middle finger is, and our 3rd priority is where our index finger is, so that's 1, 2, 3. That is going in the clockwise fashion in this perspective here, clockwise, which makes it the R isomer. Okay. Now that I've shown you that, and now that we've looked at that, I want you to go back and identify, double check, prove to yourself that you can correctly identify the carbon with the OH attached to it and the carbon with the isopropyl group attached to it as being the R and the S. Okay, so when you have biological compounds, you have the possibility of having many, many stereocenters. And what's interesting about biological systems is because they use enzymes to create these things, we typically only get one possible isomer. But let's look at how many possible isomers are for this steroid used in the human body called cholesterol. We have a possibility of 1 right here because this carbon is not as bonded near a double bonded carbon, and this isn't, so that gives us 1 stereocenter, 2 stereocenters, 3 stereocenters, 4 stereocenters, 5 stereocenters, 6 stereocenters, 8 stereocenters available to us. If there are 8 stereocenters, that's 2 to the 8th possible isomers, which means there's 256 stereoisomers possible. However, the only stereoisomer that we have in our human body is this particular 1 stereoisomer. It's the only one that's biologically active. So that's very interesting. Even though we have the possibility for 256 possible stereoisomers, only 1 is metabolized by the human body.